Okay, let's work example 9.7, the ballistic pendulum. Hey, this problem is quite common. This is a kind of a classic physics problem where you shoot a bullet into a block of wood and then you watch that block of wood swing up. And so this, the reason they like this problem is that it involves a collision, conservation of momentum, and then after it starts swinging, it involves conservation of mechanical energy. So there's two big concepts in this problem in one. So on the AP test, you'll find that most of the free response questions do that. They'll have two or three major concepts in one problem they have to use. So let's do it. The ballistic pendulum here is an apparatus used to measure the speed of a fast-moving projectile, such as a bullet. A bullet of mass M1 is fired into a large block of wood of mass M2, suspended from some light wires. The bullet embeds in the block, and the entire system swings through the height, a height of h. So you can see here, there's your height h right there. How can we determine the speed of the bullet from measuring h? Okay, so, and notice that this is all in terms of variables. There's no numbers here. And the higher you go in physics, the more that's going to happen. So let's write out what's given. Okay, so we've got, here's the ceiling or whatever, and here's our block of wood. And we'll call that, as the book did, M2. Here's a bullet, and it's moving towards the block. We'll call that M1. And we will call this velocity V1. I guess we'll call that A. That's what the book did. And then it fires into the block. It impacts the block, and it gets stuck in that block. And now the block is given a certain velocity, and we'll call this velocity B. It's hooked up to these wires, and these wires swing up so that the block comes up to a height. Let's see here, like this. Hope I can, not drawing this very well. Should have drawn the block first. So here's the block, and these wires swung up to this height, and it gained a certain height, like this, and that's h. And we'll call this state C. So we have state A. A is what the problem is doing before the block, or before the bullet impacts the block. B is the block just immediately after the collision. And C is the block when it's no longer moving and it's at its maximum height. And so what we want to find is this. We want to find the velocity of object 1, the bullet, as a function of the height. Okay, and and also you'll need to, in terms of the masses, in terms of the given quantities, the masses and the height, what must have been the initial velocity of that block. Okay, so let's solve this. Well, let's start off with the collision. And quite often you won't see yourself all the way to the solution of a problem. Just start off with something that you know is true. When this bullet hits that block, momentum is conserved. So P initial equals P final. Okay, that's my strategy. What do I know is true? Momentum is conserved during the collision. When you go from state A to state B, this is true. And so this becomes M1 V1A, and that's it. Because initially this block isn't moving. All the momentum is in that bullet. Now, after they collide, we've got they are moving together, so they have the same final velocity. But we'll go M1 plus M2. And we'll call this is the velocity after the collision. We'll call that velocity B. Okay, so now we have an expression with velocity 1. I can solve for velocity 1. Let's just go ahead and do that. Okay, so we have this expression now. And this is the expression for the velocity of the bullet in terms of the velocity of the block and the masses. But that's not what I want. I want it to be in terms of the height. So what I need to do is get rid of this guy and express the velocity of this in terms of the height. Well, if you look at this problem, when you go from B to C, the only force doing work is the force of gravity when you're going from B to C. Now look, from A to B, there was a great deal of loss of mechanical energy. There was a lot of friction. This bullet is probably pretty hot when it embeds itself in that block. But that's not what we're talking about. We're going from B to C. Once the block is embedded, the bullet is embedded in the block is starting to move. Then after the collision to this state, say from B to C, mechanical energy is conserved because the only force doing work is the force of gravity. So going from B to C, we're going to say that how about instead of initial and final, I'll say the mechanical energy at B must be equal to the mechanical energy at C. See what I did there? Instead of using initial and final, I use B and C. Does that make sense to you guys? Okay, flag me down if you're not staying with me. Now, what is the energy here? It's all kinetic energy. It's 1/2 the mass of my system, which is M1 plus M2, times V sub B squared. So this has kinetic energy. What happens to all that kinetic energy at the end? At C, it's all gravitational potential energy, which is M1 plus M2, mgh, right? mgh. Aha! Now I can get an expression for the velocity at state B in terms of the masses and the height. Let's do that. First of all, the masses cancel. And then you can multiply both sides by 2 and take the square root. So the velocity of B is equal to the square root of 2gh. Oh yeah, that makes sense. We've done that before. All the gravitational potential energy all the kinetic energy turned into gravitational potential energy, and this is what we get. So now all we have to do is plug that in here, and I'm done. So the velocity is equal to m1 plus m2 divided by m1 times the square root of 2gh. And that's what I wanted. I wanted an expression for the velocity of the bullet in terms of the height that it actually goes. Of course, you'll have to know the mass of the bullet and the mass of the block, and you're on Earth, so you better use the 9.8 meters per second squared. Okay. And let's see. Oh, yeah. That's all we. So I think that was a little bit brief, more brief than what's in the book. Let me zoom out so you can see the whole thing. Okay. Any questions on this? All right.